Hello all, welcome to this session. In the last session, I was discussing on the signal and system type of testing, how each one has its merits and how to combine both the signal and system analysis outputs in solving real life vibration related issues. Moving on, it is now good to see how a system analysis approach is taken and why this method is better. And the typical word we all know would be used is the modal analysis. In the simplistic term, a modal analysis is analyzing the system characteristics in terms of mass, stiffness, natural frequencies, damping, and such other factors. And this is more either by finite element modeling or by an experimental approach. For today's session, I would start with some history of modal analysis and its importance and what is really modal analysis. Given that this subject area is vast, it would take few sessions to cover most of these topics, and I promise to cover all of them. So, to begin the history of modal analysis, going by what we find on the net, in around 1965, James Cooley of International Business Machines, along with his colleague John Tukey of Princeton, published a paper describing how to calculate Fourier transformation on a computer. What is this? Anything surprising? Yes, because Fourier transformation or the algorithms or the calculations or the formula used till then were all on the paper, in the sense put formula, use those inputs, work on long steps of arriving at the Fourier transformed values from any time domain signal. But this is for the first time ever it was conceived or it was proved that a computer platform could be used to get Fourier transformation done. This also gave one other important feature too, that because this is solved or transformed on a computer, all that inputs that are considered would, all this time data that we consider would look like zeros and ones, which are typically the numbers. So the moment this is proved that numbers are crunchable or crunched to arrive from time data to frequency data or the Fourier transformation, this had a big acceptance in the industry, in the research institutes, academia, and so on. So this became quite popular that a lot of people started experimenting and developing the methodology. Around 1965 or so, the University of Cincinnati opened or started a structural dynamics research center to further prove this Fourier techniques on computer. And the first thing that they used was to analyze the machine tool chatter, which was so important and technically challenging at that point of time. This was mostly for the American aerospace, the American Air Force. This advancement that Structural Dynamic Research Lab made with Cincinnati University, they also shared a lot of this development with other universities across Europe and Americas. One of the important university that took part and shared a lot of this developmental activity is the KU Leuven University in Belgium. Incidentally, I was also a student of this university when I worked for LMS International earlier. So moving on, around 1968, the NASA, the National Aerospace Administration, conceived its own structural dynamic analysis model or the computation model and called it as the famous NASTRAN that we know, typically known as NASA structural analysis. So there were the simulation model and the mathematical model that uses this and the algorithms required to solve structural issues, structural behavior, structural properties, more and more came into being. Later we know ANSYS and other such solutions also are in use now. But other than the software tools and the algorithms and the mathematics and the R&D going on around these algorithms, what really triggered the widespread use of modal testing and system parameter identification is on the other side with piezoelectric accelerometers and impact hammers and small electrodynamic shakers also being conceived around 1973 75, wherein a lot of companies like Bruel and Kerr, Kiesler and others started manufacturing tiny, very rugged, versatile piezoelectric accelerometers that could be very well suited, that are very well suited and can be applied to a lot of practical real life testing in aerospace, space, automotive and so on. So the further progression is around 1984 or 85, where the great famous Professor Ivins wrote or published a paper on model testing, theory, practice, and applications. And this triggered another set of people, both putting products together in the sense computer based or a Unix based platform along with data acquisition system to be first time called a combined system for data acquisition and further processing, even though the basis was this Fourier transformation, but integrating a hardware front end, which is typically where accelerometers are connected from the system to be tested, could be a car, could be an airplane or so on. And this integrated with a computer software system or a computer platform where data is realized, processed, and the rest of the outputs are also visualized or brought into use. So this significantly changed the way the model testing and the system parameter establishment were being carried out till then. What started with about 4 to 16 channels of physical data acquisition, mostly from Hewlett Packard, Agilent Technologies, SCADAs and so on. Now we see well over 1,000 to 2,000 channels simultaneously that can work when deployed for large testings like the satellites, the rockets and the airplanes. So what has combinedly developed is the overall development in electronics, the memory, the system handling capabilities, the computational speed, data crunching speeds. So put together, the entire structural testing and the model analysis domain could develop as the demands rised. As like in normal, most of these application areas were in space, aerospace and automotive engineering. But for me, I would say most of the real encashment of this technology happened with airplane testing and in automotive. And automotive even today continues to use experimental model testing, finite element based model testing as their kind of primary tool in getting all the system characteristics for a new design, for remodeling of a design, re-evaluating and so on and so forth. So with this background and some kind of history, there could be more about this history, but I jumped few just to give a cursory look of it. Let's move on to just getting the first glimpse of what is really modal analysis. Modal analysis is the process of determining the inherent dynamic characteristics of a system in the forms of natural frequency, damping factors and mode shapes sometimes. We also call them together as eigenparameters or eigenvalues when it is referred to in mathematical domain. And this parameters that we obtain and then use them to formulate a mathematical model would be for its dynamic behavior. So the formulated mathematical model is referred to as the modal model, and the system and information for characteristics are known as the modal data. It really is not too different from understanding how somebody tests a natural frequency of any given system. We all know how a tuning fork was tested and its frequencies were identified. We have seen this in our college days, but on an enlarged scale that you now put to establish the entire system characteristics. This I said before also, that you need to identify the properties of the system in terms of the natural frequency or frequencies, and for each of those resonant or the natural frequency condition, what is the damping characteristics of the system, and how for given any of these natural frequencies the system is going to move. So it's a frequency specific movements or the deflections or the shapes of the system that's being tested. So this can be on the mathematical side. These solutions are seen in partial differential equations of continuous such in beams and in strings that we see. This method is directly applied. So in a nutshell, the modal analysis uses, if it's experimental or even in a finite element, it will establish the boundary conditions, which when I say that, we will cover more of this in the coming sessions. So both the finite element and the experimental modal models consider how the boundary condition should be. Is this fixed? Is it a free and or is it a combination of fixed and free? Then you will introduce a set of forces, as we also can call it as a matrix of forces, and then expect a certain output in terms of the dynamic response. Typically it could be vibration, there could be other parameters. So now once this is done, a set of forces are introduced, your system is in a controlled boundary condition, and then outputs in terms of vibrations or maybe acceleration, for example, are quantified. You build a system matrix, which is to say a set of forces going in and a set of vibration outputs coming out of the system. Now the entire process of a modal model or creating the modal model is of establishing what you see as these natural frequencies are correct, and for each of the natural frequency the correct determination of damping, which is typically the force within the system to resist the force coming into and then bringing the system into its normal equilibrium. So that's one other very important parameter. So put together, the entire activity is exciting the system under test with known boundary conditions or wanted boundary conditions, then get a set of output and then now relate the output vibration data to the input forces and create a modal model. I know for sure that this is a very, very generic information and the imagination of what a modal analysis would be, but in the coming sessions we would describe this in a more descriptive way, giving examples, giving some amount of mathematical background, and try to explain as much possible and as much that could be grasped by the viewers. Thank you for watching, and we will see you soon in the next session.